Hi there, welcome to this video. It is the next in the series to help you revise for your Maths A-level this summer. I hope revision is well on its way and going well. And in this video, I'm going to break down integration, give you an overview of all the different skills you need, and then look at some harder past paper questions. Because in the old spec in the C4 exam, up to about a third could be on integration. In the new spec, it is less than 20%, but it's definitely worth getting to grips with, because once you have mastered recognizing the different types, they will get easier. It is now the modeling questions that can take up to a third of the paper. So in my next video, I'll have a look at modeling. So be sure to like and subscribe, check out the channel for what I hope is helpful videos for all your maths exams this summer. So when you see an integration question, don't panic. I'm going to break it down to about 10 skills. So if you're confident and happy with all the different skills you need, you can use the timestamps in the description to just go directly to the harder questions, which are towards the end of the video. Okay, let's get started. So of course, integration is the reverse of differentiation. When we are differentiating, for example, 5x squared, you take one off the power and you multiply by the old power, and that would give us 10x. If we were integrating 10x, we need a system to get back to the 5x squared. So we are going to add one onto the power to get back to the 2, and we're going to divide by the new power. So it would be 10x squared all over the new power 2, which would give us the 5x squared. Now we also have to have a constant of integration if we've got indefinite integration and we've got no limits on the integral, because just in case we were differentiating, for instance, 5x squared plus a constant, say 3, that constant would go out in the differentiation, so we need to have the c there just in case there was a constant, and then with some more information in the question that would allow us to find c. Now, if we did have some limits on our integral, say between a and b, then that is definite integration, and we are finding the area between those two limits, a and b, and the integral sign is actually a sum sign because you are summing up all those strips that are y high. So if I just made one of those strips bigger, then the width of the strip is dx and the height of the strip is y. So when we write y dx, those two are next to each other and stand for the fact that we are finding the area of a rectangle, which is just those two terms multiplied together. Now when we do the add one on and divide by new power, you don't actually do anything with the dx, but you do need it there in order to integrate. So let's start to have a look at the different skills you need when you're going to integrate, and number one is looking at standard results. So this is the page from the formula book. On the page you've got an integration section. So for example, sec squared, you get that integrates to tan x. The k is just standing for a constant. What happens to that constant? It goes 1 over k on the front. So you get all those standard integrals. You also get the by parts formula here, and then on the same page you get some differentiation, because that is going to be useful. For example, if we know that cot differentiates to minus cosec squared, if I was asked to integrate cosec squared x, then I could just reverse that, and I know that minus cosec squared goes to cot, so positive cosec squared goes to minus cot x. The next skill I'm going to have a look at is being able to recognize the chain rule and be able to apply it in reverse. So when do we use the chain rule? We use it when we are differentiating. So let's have a look at it going forward, because that will help us to understand what's going on when we're working backwards. So if I had, for example, y is equal to 3x plus 1 all squared, we can tell we're going to be using the chain rule because we've got a function of a function. We've got an inside function, the 3x plus 1, and an outside function. Now instead of calling the inside function u and saying u squared and making a chain, we speed it up because the pattern is that we differentiate with respect to the outside. So what's on the outside? The squared. How do we differentiate with respect to something being squared? We would power down and take one off. We've left alone on the inside, so now we need to differentiate with respect to the inside, which would be a times by 3. So tidying up, that would be 6 into 3x plus 1. Let's do a couple more examples here. If we had y is equal to the ln of 3x, again we've got an inside function, the 3x, and an ln. So dy by dx, differentiate with respect to the outside, so ln differentiates to 1 over 3x, leaving alone on the inside, and then differentiating with respect to the inside, so that would be times by 3. Those 3's would cancel, so that would actually equal 1 over x. Now be careful, because let's have a look at y equal 3, the ln of x. That would actually differentiate to just 3 over x. So wouldn't have to apply the chain rule. That 3 is just going to join in. It's 3 times the ln of x, so it's 3 times the differential of ln of x. One more example here. Let's do y is equal to the ln of x squared plus 3x plus 4. Now dy by dx, differentiating with respect to the outside, leave alone on the inside, would be 1 over, just treat the inside function as if it was x, then because it wasn't, we multiply by the differential of the inside, which would give us 2x plus 3. So we can write that as 2x plus 3 all over that denominator, x squared plus 3x plus 4. Okay, let's have a look at how this is going to work when we are integrating. So for example, if I was to integrate 2 sec squared 3x plus 1, we can tell we might be using the chain rule, because again we've got an inside function and an outside function. A 2 there on the front could possibly be taken outside. It's going to just be 2 times the integral of all of that. So when we've got this situation, think about the outside function first. Sec squared integrates to tan. So again, leave alone on the inside. The 2's just going to join in. And then think via the chain rule, if I was to differentiate that, would it get me back? I would be writing 2 sec squared 3x plus 1. That would be differentiating with respect to the tan, but then I must multiply by the differential of the inside, so by the chain rule would cause me to times by 3, so I need to divide by 3 to compensate for that 3 that's going to come from the chain rule. Integrals of the form where you've got the differential being multiplied by the same function. For example, if I was trying to integrate cos x sine squared x. So the cos x is the differential of the inside function. So again, think about the outside function first, and if we're integrating, we're going to add one on. So it would be sine cubed x and divide by the new power. Now think, if I had y is equal to a third sine cubed x and I differentiate, does that get me back to here? I would power down, take one off. That's differentiating with respect to the cube, and then I would multiply by the differential of the inside function. So it's going to get me back to the question. I didn't have to do anything. The cos x was just going to come via the chain rule. So that is my final answer. Just 1/3 sine cubed of x. Now similarly, what we got over here when we were doing the ln's, when you've got the differential in the numerator and the main function in the denominator, for example, if I had to integrate x plus 2 over x squared plus 4x minus 1, you are looking for the differential to be on top, and then it will be ln's. Now here the differential of the denominator is 2x plus 4, and I've actually got half of that. So you can manipulate it, and just as long as it's only with a constant, not the variable. If I want to have the double on the top, I can just put a 2 there. And now I will have the differential on the top, but I've made the integral twice as big. So to compensate for that, I will do half. Now that half is just going to join in like the 2 did up here with the sec squared. And then the answer is going to be a half the ln of x squared plus 4x minus 1. Because if I differentiate that, the half's going to join in. I'm going to go 1 over that inside function, and then I'm going to multiply by the differential, which is sitting there on the top. The next skill I'm going to have a look at is using trig identities. So the one that you should know from lower 6 is that sine squared plus cos squared is equal to 1. Now if you just imagine cos squared sitting underneath all of those, so dividing throughout by cos squared, sine squared over cos squared would give tan squared x, cos squared over cos squared would give you 1, and 1 over cos squared is sec squared. So you can quickly generate that one, because we would use that if you were asked to integrate tan squared x, for example. You would just be integrating sec squared minus 1, and sec squared integrates to tan x. So you could use that one. If we wanted to generate the other trig identity that comes from this top one, if you imagine just sitting underneath each of those, sine squared over sine squared is 1, cos squared over sine squared is upside down tan, so that would be cot squared x, and then 1 over sine squared is cosec squared x. So you can quickly generate these other two identities from just knowing that one from your lower 6. Okay, the other identities that we use when we're integrating is cos 2x. Now cos 2x has got 3 versions. It's got cos squared x minus sine squared x. Then replacing the cos squared with 1 minus sine squared, we would have 1 minus 2 sine squared x. And then the other one, replacing the sine squared, would be 2 cos squared x minus 1. So we would use this when we are integrating even powers of sine or cos. So for example, if I was asked to integrate sine squared x, then I want to use this version of the cos 2x. So cos 2x is equal to 1 minus 2 sine squared x, and then what we do is make that sine squared x the subject. So we swap them over. 2 sine squared x will equal 1 minus cos 2x, and then sine squared x divided by 2 would be a half minus a half cos 2x. So instead of integrating sine squared, we just replace the sine squared with what it's equal to in terms of the double angle. It is 1/2 minus a half cos 2x, and that will integrate to a half x. Cos 2x would integrate to sine 2x, but then from the reverse chain rule, I'd be also timesing by a half, so that would be minus a quarter sine 2x. Now when we're integrating odd powers of sine or cos, so for example, if I was going to integrate cos cubed x, we write that as the integral of cos x cos squared x, and then that's going to be cos x, and then replace the cos squared with 1 minus sine squared, and then multiply the cos x in, so that would be cos x minus cos x sine squared x, and now we can integrate. cos is just going to integrate to sine x, and then here from the reverse chain rule, this is just going to be minus 1/3 of sine cubed x. So that's how to integrate odd powers. And then you've also got to be really good at spotting the double angle theorem for sine x. So if we have sine 2x, that's equal to 2 sine x cos x. So if you see a sine times a cos, for example, if I was asked to integrate sine 3x cos 3x, I've got this situation where I've got those two being multiplied together. So if you've got the angles here are single, it's going to be double over here. So if I had 2 sine 3x cos 3x, I would have sine 6x. So whatever those angles are there, it is double here. So I'm trying to integrate this but half of it. So I will have half here would then give me what I'm wanting to integrate. So I'm integrating 1/2 of sine 6x. So that is going to be sine integrates to minus cos 6x, and then I'd be dividing by 6, which will times by the half, so it's actually going to be minus 1/12 cos 6x. Now I'm going to have a look at partial fractions, and it's really nice when the question is set up with the A being even C, so you know exactly what type you're dealing with, but sometimes it's not set up like that, and you need to know that when you have this situation, for example, when you've got a single fraction, then it's going to be much easier to integrate if we actually split it into the partial fractions. So because this is linear denominators, it would be A over the x minus 1 plus b over x plus 2. Then go through your routine to find a and b, because then the integration is going to be much easier when you've got the separate fractions. So there's 3 different types. That's the first type, when we've got linear factors, when you've got a repeated factor in the denominator. So there, that squared means we've got a repeated factor. You would set this up as a over the repeated factor, and then just in case there was also the single factor, you need to allow for that as well, plus c over the other linear, x plus 3. And then sometimes we would have top heavy. So even when the powers are the same, that is top heavy. Now if we did the algebraic division, we are dividing x squared minus 1 into x squared plus 4. Now when the powers are the same, we're going to have less lines in our algebraic division, because x squared will go into itself a whole number of times. So you're not going to have any algebra on that top, you're just going to get a whole number. If we had, for instance, an x cubed minus 4 divided by the x squared minus 1, if we set that one up, x squared minus 1 into x cubed minus 4, well, x squared into x cubed would get x. So you're going to have some algebra on the top. So you're going to have more rows of your algebraic division. So depending how far those numerator and denominators are away from each other is how you would set your partial fractions up. But doing the algebraic division, x squared into x squared goes one time, multiplying by everything on the front and writing it underneath so we can get the remainder. 4 minus minus 1 is going to be 5, so I know this goes a whole time plus a 5 over, and then because I can see this is the difference of 2 squares, I would write that as x plus 1, x minus 1, and then I would have to split this up into partial fractions using the linear factors method. Now you could, instead of doing the algebraic division to get that number on the front, you could just say that this is going to be x squared plus 4 over the x squared minus 1 is equal to our a plus the b over the x squared minus 1. And going clear of fractions, we'd get x squared plus 4 is equal to a into x squared minus 1 plus b, and then to get that 1 that we got there, we can see comparing coefficients that a has to equal 1. So let's have a look at a question that involves partial fractions, and in this question it's asking us to express in partial fractions. We can see we've got a differential equation, and the fact that we're doing this in part A is going to help us in part B. Now it doesn't always ask us to do that in part A. When we get to the part B part, we might have to just know that we need to do partial fractions, but it is in this case, so let's set it up. It's 1 over p into 5 minus p, two linear factors in the denominator, so that's going to be a over p plus b over 5 minus p. Go clear of fractions by multiplying throughout by that common denominator. We'll get 1 is equal to a with the denominator it's not got plus b p. Now we let p equal something that will make the a or b term go out, so let p equal 0, we'll lose the b term, we'll still have 1 is equal to 5a, which tells us that a is equal to 1/5. Now let p equal 5, then we'll have 1 is equal to 5b, which tells us also that b is equal to 1/5. So let's put them back into the positions. Now we've found them. So rather than putting 1/5 there in the numerator, what's going on, if we just take this first term, we've got 1/5 divided by p, just rather than putting it underneath, putting it like that. And when we divide with fractions, we are going to times and turn the second one upside down. So really that 5th in the numerator is just going to join in with the denominator. So rather than writing them like that, just put the 5 underneath, and that's how it will look in our partial fractions. Now in part B, we're told that this differential equation is modelling the population of meerkats. P is in thousands and the meerkats is measured in t, time measured in years since the study began. Now given that t is equal to 0 and p is equal to 1, we're being asked to solve the differential equation and get it in this form. So what do we do when we solve differential equations? We're going to separate the variables and integrate. So all the p terms are going to cross multiply and come down. So we're going to have 1 over the p into 5 minus p dp is equal to 1 over 15 dt. Now this is where the partial fraction work that we've done in part A, we're going to replace this with the integral of 1 over 5p plus 1 over 5 into 5 minus p. And what we can do here is we can take a factor of 5 out. So I can put these fifths on the front, and I can even here take a factor of 5 out here, and then I can just cancel by the fifths on the front, so that will make life easier for myself. And now can go ahead and integrate. So 1 over p is going to integrate to the ln of p, and then it'll be the ln of 5 minus p, and by the chain rule we'll then have to compensate for the fact that we'll get a minus when we differentiate, so we'll have a minus there, is equal to 1/3 of t plus c. Now that integration constant we're going to be able to find by subbing in these values, that t is equal to 0 and p is equal to 1. So the ln of 1, which is 0, minus the ln of 5 minus 1, which is 4, is equal to t being 0 will go out, so that will be equal to c. So c is equal to minus the ln of 4. So now let's write our differential equation. It is the ln of p minus the ln of 5 minus p is equal to 1/3 of t minus the ln of 4. Now I want to get all our ln terms to one side, so taking this to the other side it'll be plus, and we can see by our log laws the plus ones are going to give me the ln of, multiply them together, 4p divided by the one that's minus, 5 minus p. And that will equal 1/3 t. So when I've got it as a single log, I can just take e's to both sides and they will cancel, and I will have that 4p over 5 minus p is going to equal e to the 1/3 t. And now I need to make p the subject, so I'm going to cross multiply. 4p will equal e to the 3rd t times 5 minus p. I need to multiply those in. So 4p is equal to 5 e to the 1/3 t minus p e to the 1/3 t. Collect all the p terms to one side and take p out as a common factor. I'm going to have p into 4 plus e to the 1/3 t is equal to 5 e to the 1/3 t. And then we've got p on its own, so p will equal 5 e to the 1/3 t divided by 4 plus e to the 1/3 t. Now that's not quite in the format that we want it. In the form we want it, we want an a and a b and something to the minus, and this is minus 1/3 t. So what we do to get that is we divide each of these terms by e to the 3rd t. So we'll have p is equal to 5 e to the 1/3 t over e to the 1/3 t divided by 4 over e to the 1/3 t plus e to the 1/3 t divided by itself. So if you're doing the same throughout to each of those terms, then you're keeping the fraction in the same proportion, and what's going to happen is these will cancel, but this e to the 1/3 t in the denominator, when we put that up in the numerator with the 4, it's going to give us 2 to the minus. So this is going to be 5 over 4 e to the minus 1/3 t plus 1. So our a is going to equal 5, our b is equal to 1, and c is equal to 4. Now you do that sort of process of dividing by that e to the 3rd t so that we've got the term here to the minus, because p was equal to 5 over 1 plus 4 e to the minus 1/3 t. And in this form it helps us to see what's going to happen as t gets big, because when you have to the minus here, an exponential graph that's to the minus comes down, and as t is going to get big, this term here is going to tend towards 0. So our population, as t tends to infinity or gets big, the population is going to tend to 5 over 1 plus, now this is going to go and never reach 0, so it's going to plus 0.0000, something very, very small. So this is going to mean that the population is never going to exceed 5,000. We're never going to have 5,000 divided by 1 exactly, it's 1 point something, so the population will not exceed 5. And remember our question, p was in thousands, so that's going to not exceed 5,000. The next skill is using substitution. I haven't seen very many questions where you have to choose your own substitution. We've talked already about the inside function. That is usually what you're going to choose for you, but there's no hard and fast rules, and you can even do the same question by doing different substitutions. You're still going to get the same answer, but for this one you'd maybe use that u is equal to 1 plus sine x, and for this one you'd maybe use u is equal to x squared. Now when you're integrating, you have to replace everything that's being integrated. You have to replace the dx, and if there are any limits, you have to put them in terms of u as well. Next, I'm going to have a look at algebraic division, and I'm going to do that via this substitution question, because when I make the substitution, algebraic division is going to help us to integrate with respect to u. So when you're substituting, you have to substitute for the dx, we're going to have to substitute for root x, and we need to substitute for the limits, which at the moment are in terms of x. So the substitution we're being asked to use is that x is equal to u squared. So I like to get the dx on the go first. So dx by du is going to be 2u. Cross multiplying, dx is worth 2u du. So next I'll do the limits. When x is equal to 4, well, if x is equal to u squared, then root x is equal to u. So all I need to do is root 4, so u was going to equal 2. When x is equal to 0, u is also going to equal to 0, and then this root x here is just going to be u. So now I'm ready to make the substitution. I'm going to be integrating in terms of u between 0 and 2 of 1 over 2 plus u, 2u du. Now the du is going to mean I'm going to integrate with respect to u, but this 2u needs to join in with what I'm integrating. So I'm going from 0 to 2 of 2u over 2 plus u. Now this is in fact top heavy because the powers on the numerator and denominator are both the same. So this is where the algebraic division is going to help us. Now when we do an algebraic division, we normally like to have the algebraic term first. So 2 plus u is the same as u plus 2, and we're dividing that into 2u. So take the u and divide it into 2u, and that'll go twice. An answer on the top times by both the terms on the front, that will give us 2u plus 4. Do a takeaway to get the remainder. We're going to get minus 4. So I'm going to be integrating between 0 and 2 of 2 minus 4 over u plus 2. So now I can integrate. That's going to be 2u minus 4, the ln of u plus 2. And now I need to put in my limits. So when u is 2, I'm going to get 4 minus 4, the ln of 4. Put 0 in, I'm going to get 0 minus 4, the ln of 2. So here the ln of 4 is the same as the ln of 2 squared, and then that squared can come down and multiply by the 4. So it's going to be 4 minus 8, the ln of 2, minus 0 minus 4, the ln of 2. So it's going to be 4, and then we've got minus 8, the ln of 2, and then this minus will make a plus. So 8, the ln of 2, or minus 8, the ln of 2, plus 4 is going to be minus 4, the ln of 2. Next, I'm going to have a look at integration by parts, which is a product rule for integration. So when you have two expressions being multiplied together, you say that one of them is u and one of them is something I've already differentiated, and we can call that dv by dx. Now you get the formula on the formula sheet, so you can see we need uv, so we're going to have to integrate what we've called dv by dx to get the v, and we also need a du by dx, so we're going to have to differentiate the u. So you need to have your wits about you because you're going to be integrating and differentiating in the same question. Now by parts is what we use to actually integrate the ln of x, which is not two things being multiplied together, but we can rewrite that as 1 times the ln of x. So there's an acronym in order to help you to decide what's going to be u, and that is LATE. So L stands for logs, A for algebra, T for trig, and E for exponentials. And we can see here we've got some logs, so that is going to be what we're going to call U. So U will be the ln of x, and we do this because we do know how to differentiate ln. That's just going to be 1 over x, and so dv by dx will have to equal the 1, and then integrating 1 we're just going to get x. So the integral of the ln of x is going to be uv, which is these two multiplied together, x, the ln of x, minus the integral of these two multiplied together. So that is 1 over x times x. Now these x's will cancel, so it's going to be x, the ln of x, minus the integral of 1, which is just x. Next, let's have a look at parametric integration. So if we're trying to find the area trapped between two limits on the x-axis, so we'll be integrating with respect to x, and our limits will be the values on the x-axis. If we are given our curve in terms of a third parameter, say t, we can integrate and we can find the limits in terms of t from the x equation. We can put the y equation in terms of t, and then as long as we multiply by dx by dt, so we'd have to differentiate the x equation, and then that will allow us to differentiate with respect to t, because when we fill in the differential here, informally these dt's will cancel, and we will actually be finding the area under the curve because we'll have y dx. Let's have a go at a parametric integration question. We've got this curve being given parametrically in terms of theta. We've got the point P, which is K8, and in part A we're being asked to find what K is. Now what's happening at K? At K, y is equal to 8. So if we let y equal to 8, 8 will equal sec cubed theta, and then if we take the cube root, 2 will equal sec theta. Sec is 1 over cos, so a half is equal to cos theta, and then inverse cos of a half, theta is going to be pi by 3, and then we want the x value when theta is pi by 3, so x is going to equal 3 times pi by 3 times the sine of pi by 3. Pi by 3 is 60, sine 60 is root 3 over 2. These 3's will cancel, so x is going to be pi times root 3 over 2, and that is what k is equal to, root 3 over 2 pi. Now in part B, it's asking us to show that the area can be expressed in this integral here in the form where we are integrating with respect to d theta. So we're going to have to do our parametric integration. So if we were going with the x values from 0 to k, and k is our root 3 over 2 pi of our y dx, then transferring it in terms of theta, it's going to be 0. Now what was theta when x was the root 3 over 2 pi? Theta was our pi by 3. So it's pi by 3 of y being given parametrically, which is sec cubed theta, times dx by d theta. So we go over here, dx by d theta, I can see I've got a product and I'm going to have to use the product rule. So it's going to be first differential of second, which is cos theta, plus second differential of first, which will be 3 sine theta. So I need to times that here, 3 theta cos theta plus 3 sine theta, and then it's going to be d theta. So in order to get this expression, I need to multiply these in. I can see I can take a 3 out, So that's going to be 3, the integral between 0 and pi by 3. Now when that sec cubes goes in, sec is 1 over cos. So you're going to have cos on the top and then sec cubed on the bottom. So that's going to be theta sec squared, because the sec cubed, one of the coses will cancel on the bottom, and then plus, when this times is here, you've got sec cubed, which is 1 over cos. So you've got sine theta over cos cubed theta, and one of those coses can act with the sine to make a tan theta, and then you'll have cos squared left on the bottom, which is sec squared theta. So is that what we need? Yeah, theta sec squared and tan sec squared. So here my lambda is equal to 3, alpha is equal to 0, and beta is equal to pi by 3. Part C is asking us to now hence integrate. So we found that lambda was 3. The integral went from 0 to pi by 3 of theta sec squared theta plus tan theta sec squared theta d theta. So this first term we're going to integrate by parts. And the second term, we can see we've got the differential with a function, so we can do that via the reverse chain rule. But first of all, by parts, using the acronym LATE, the algebra is going to be the theta, so that's going to be u. So u is equal to theta. dv by d theta will then be the sec squared. So we need to differentiate the u. So that's going to be 1. Integrating the sec squared will give us tan. And then let's start to integrate. So we'll have 3 on the outside. The by parts formula, it's these two multiplied together. So that's theta tan theta minus the integral of these two multiplied together, which again will just be tan theta. And then we've got plus. Now if I think of this as the main function and do half tan squared theta, then by the chain rule I'd power down, leave alone, but then the differential of tan is sec squared, so I'll get the sec squared from the chain rule. So now all I need to do is integrate the tan theta, so I've still got my 3 theta tan theta. And then using the standard result, the integral of tan is the ln of sec theta plus half tan squared theta. And we're going between 0 and pi by 3. So putting my limits in, 3, pi by 3, tan of pi by 3, tan of 60 is root 3 minus the ln of sec theta will be 1 over cos. Cos of pi by 3 is the same as cos of 60, which is a half, and upside down of that will be ln of 2 plus half tan of pi by 3 is root 3, and that squared is 3. So that's putting the first limit in. When you put the 0 in, 0, 0 and 0, so they're all going to be 0, so that's good. And then multiplying the 3 in, we're going to get root 3 pi minus 3, the ln of 2, plus 9 over 2, and that is my final answer. Next, we're going to have a look at integrating a to the x. So what we do here is we say it's the same as integrating e to the ln. They would cancel each other out, a to the x. So we haven't done anything because e and ln are inverse of each other. So we've still just got a to the x. And then by the log laws, that's the same as bringing that down in front. E to the x the ln of a. Now e integrates and differentiates to itself, but when we integrate e to the kx, that is going to integrate to 1 over k e to the kx, and what we've got here is the ln of a is just going to be our constant k, so that is going to be 1 over the ln of a e to the x ln of a, and then we just reverse the log laws and take that x back up, so it's 1 over the ln of a e to the ln of a to the x. The ln and the e's will cancel back out again. We'll have 1 over the ln of a to the x, and then plus c. This next question, part 1, asks us to use the trapezium rule. The trapezium rule approximates the area, and you get the formula on the formula sheet. It's going to be a half of h of y0 plus yn, either ends, plus 2 of all the ones in between, all the way to y, the one before, and you're going to apply that in this question with just an area that has 2 strips. So we're going to need a table of values, because if you imagine we're trying to approximate the area between 0 and 4 with 2 strips, you're just going to have the middle one 2, so then that will be our 2 strips. So let's have a table of values where x is going to go 0 to 4. We need the y values. When x is 0, y is going to be a half. When x is 2, it's 1 over 2 plus root 2. When x is 4, root 4 is 2, and 2 plus 2 on the bottom is going to give us a quarter. So feeding them into the trapezium rule here, you've got half of, now h is just how wide the trapeziums are, so that's the distance along the x-axis, which is 2, times y0, which is a half, yn is the one in the end, a quarter, plus twice of the one in between, there's only one, so that's 2 plus root 2. So these 2's on the front are going to cancel. A half plus a quarter is 3/4, and then what we need to do is rationalize the denominator, so times it by 2 minus root 2 over 2 minus root 2. Now I like to do my denominators first, so that's 3/4 plus 2 times 2 is 4, and then it'll be minus 2, and then on the top it's going to be 4 minus 2 root 2, so that's 3/4 plus 4 minus 2 root 2 all over 2, cancelling that 2 into the top, 3/4 plus 2 minus root 2, and then this 2 into quarters is 8/4 plus the 3, that's going to give us 11/4 minus root 2. Now part 2 I did in the video earlier. I think that came out to be 4 minus 4 the ln of 2. So in part 3, use your answers to both those parts to say that the ln of 2 is going to be k plus root 2 over 4. So because we've got this answer here is an approximation to the actual answer, we can say that 4 minus 4 the ln of 2 is approximately equal to 11 over 4 minus root 2, and then just rearrange to get the ln of 2 the subject, so that's going to be 4 minus 11 over 4 plus root 2 is approximately equal to the 4 the ln of 2. So now just divide by 4, so that's going to be 4 over 4 minus 11 over 16 plus root 2 over 4, and 4 over 4 is 1 minus 11 over 16 plus root 2 over 4 is going to give me that my k is going to be 5 over 16. Going to do another substitution question now. So we're using this substitution, x is 2/3 tan u for this integral. So let's get dx on the go to start with. Dx by du is going to be 2/3 sec squared u. Cross multiply to see what dx is worth. Dx is equal to 2/3 sec squared u du. Now I need to substitute for x squared. So what's x squared? X squared is equal to 4/9 tan squared u. So now let's make the substitution. It's going to be the integral of 1/4 plus 9. What's x squared? It is 4/9 tan squared u. And then du is 2/3 sec squared u du. So these 9's here will cancel, and I've got a 4 and a 4, so that can come out as a factor on the front, and then you'll have 1 plus tan squared u, which is sec squared. So that's going to be good because that can cancel with the sec squared that's come from the dx. So those can cancel, and then the 4's can cancel with the 2, so 1 and 2. So really I'm just going to be integrating 1/6 with respect to u. So that's just going to be 1/6 u plus c. Now I need to give my answer in terms of x. So go back to the original substitution. If x is equal to 2/3 tan u, we need to get what u is worth. So cross multiply 3x/2 is tan u, and then we'll have to do inverse tan. So you can write tan to the -1 or arc tan of 3x/2 is equal to u, and then I just need to substitute that in. So it's going to be 1/6 of arc tan of 3/2x plus c. Thanks so much for watching. I hope that video has helped with your integration revision. Do keep an eye out on the channel because I'll put some more videos on the run up to your exams. Hope revision is going well, and best of luck if you're sitting your exams this summer, and I will see you on the next one.